Hey everybody, so we're going to do a quick video about what we call differentiability. We'll get to what that term means to be differentiable or differentiability in just a minute. But we're going to start with a basic derivative question, find the slope of the line tangent to the function. And so one of the things we want to recognize right away, of course, is that when we talk about the slope of the tangent line, we're talking about the derivative. And so if we have a piecewise function, we need to take the derivative in two separate pieces. And so we'll do both of those. I'm going to walk through each of these derivatives using the definition of the derivative. So we'll say for x less than or equal to 0, f prime of x should be the limit as h approaches 0 of x plus h squared plus 1 minus x squared plus 1 all over h. So we're just going to do this using the definition of the derivative here. So with that definition of the derivative, we have f of x plus h minus f of x all over h. Just our slope formula where we have a limit to make the distance between the 2 points, which is h, become 0, giving us the slope of a tangent line instead of the slope of a secant line, giving us an instantaneous rate of change instead of an average rate of change. So now we just need to simplify this, and there's really only one thing we can do here, which is just to expand out this binomial, FOIL this guy out, if you want to call it that. So we have, I know that I can't do direct substitution, so I'm still working with my limit. This is going to be x squared plus 2xh plus h squared minus x squared. Make sure we distribute our negative, minus 1 all over h. Some stuff cancels, that's nice. Cancel out the x squared. Oops, forgot to write the plus 1. I knew it was going to cancel, so I just forgot to write it. Plus 1. That's just this little guy here. He cancels. And so then everything that's left in the numerator has an h in it. Everything that didn't have an h got canceled out. So that means if everything has an h, I can divide out that h from the denominator. And now, because h approaches 0, I can plug in 0 for the one remaining h. We'll write it out. We did a lot in that step already. Let's go ahead and write it out. Limit as h approaches 0 of 2x plus h. This h got canceled out. We only canceled out one of the h's here, so we still have this one left. So now I can plug in 0 for h, and I no longer have undefined because the h in the denominator went away. So then we have, let's move this all up just a tiny bit here. So then we have, if x is less than or equal to 0, then f prime of x equals 2x. Which again, what that means is that for any x value that I plug in less than or equal to 0, if I need to know the slope of the tangent line, I'm going to plug it into this equation here. So they wanted me to find the slope of the tangent line for x equals negative 1, x equals 0, and x equals 1. Well, these first two are less than or equal to 0, so I'm going to plug those x's in to this derivative that I just found. F prime of 0 is equal to 0, and f prime of negative 1 is equal to negative 2. Now I need to do the same thing, but I can't plug in positive 1 to that derivative I just found. I have to figure out what the derivative is for the other piece of my piecewise function. Now fortunately, this is a very simple function that they gave us. So I'm actually going to skip all this lovely work because I know that the slope of this piece, no matter what x I plug in, the slope is always 1. This is a linear function. It always has the same slope, as opposed to my parabola here, which has a different slope depending on which x I plug in. So here, the derivative is just 1. I can just think about that. Now, I could go through this work and I would arrive at that conclusion, but we can be smart and say, well, hang on, I need that derivative to figure out the instantaneous rate of change, the slope of the tangent line, because it's different than the average rate of change. It's different than the slope of the secant line. But for the second piece here, I don't need that. So, for f, or sorry, not for f, for x greater than 0, f prime of x is just 1. And thus, f prime of 1 is 1. So that's kind of funky. We've got this piecewise situation here, and we had to think about two separate derivatives. But there's nothing really new here. We're just taking everything that we have done previously and applying it to a piecewise function. Let's write this derivative out in a piecewise manner here. Let's throw that over there. So what our derivative really is then is that f prime of x is also a piecewise function, which is 2x if x is less than or equal to 0, and 1 if x is greater than 0. Now, this leads to an important question as we think about this limit and what's actually happening at this place where we switch from one function or one piece of my function to the next. Now we have this or equal to, right? But and so that's why I plugged in the 0 here and said, well, then the slope there is 0 for f prime of 0. But that doesn't really fit my definition of a limit, and we know that the derivative is a limit. And so we should be able to be approaching x. So we should be able to approach an x value of 0 from both sides. And so as I approach 0 on the left, I'm using this piece, but as I approach 0 on the right, I'm using this. And so I'm getting two different values for my limit, which tells me that actually, this does not exist. This does not exist. Because the derivative is a limit, and if I approach x equals 0 from the left, I'm going to get 0. But if I approach x equals 0 from the right, I'm going to get 1. And we know that when the left-hand limit and the right-hand limit approach different things, the limit does not exist. And so that's the situation we have here. Because the derivative is a limit, that limit does not exist at x equals 0, where we switch from one piece to the next. Let's look at a picture to show us what's happening here. Let's get all this out of the way here. Save this chunk here and this chunk here. All the rest of this, let's make it go away. Okay. So here's a picture of the original function if I were to graph that piecewise function. And I can also, now that I have the derivative as a function, I could graph that. Let's look at that graph. So now we have them both next to each other here. Let's get you out of the way for just a second. And so you can see, here's the graph of the derivative. It's jumping. And so as I'm approaching 0 from both sides. I can have, we're talking about you've got x equals 0, and then the derivative is saying, okay, I want to take the slope of the line between 2 points and then let those 2 points get infinitely close together. Let that h, which is the change in x, become 0. And as h is approaching 0 on the left, the value of the derivative is approaching 0. But as h approaches 0 on the right, the value of the derivative is just 1 that whole time. So this derivative does not exist at 0. So I actually have to modify what I said for my piecewise derivative here. This or equal to should not be here. The derivative does not exist at x equals 0 because our slopes jump from one point to another. And that's really what this whole idea of differentiability or being differentiable is all about, which is our focus for today. So let's go ahead and write that down. So here's our definition. Go ahead and pause if you need to so that you can write that down. So a function f is differentiable at a if f prime of a, sorry that got cut off weird when we transferred over to the iPad, if f prime of a exists. So we are differentiable, and the word here is so important, this able at the end. The process of taking a derivative is called differentiation. You are literally differentiating the slope of the function at different points. When you differentiate things, you're saying what's different about parts or pieces of a group. So you're differentiating the slope of one point from the slope of another. And here we're saying we are literally, we're interested in where are we able to differentiate. So this term, just can you take a derivative and get an answer out? That's what differentiable means. So we're differentiable if the derivative exists. And sometimes you'll be asked about a particular point. Is this function differentiable at 0? Other times you'll be asked about an interval. On what interval is this function differentiable? And it's really very, very similar to continuity. It's not exactly the same, but it's very, very similar to it. If we're differentiable at a particular point, then when they ask us, okay, on the interval, where are we differentiable? You're just looking for those things that we know happen when we fail to be differentiable. And so let's look at a couple different examples of not being differentiable. All right, I'm going to go ahead and just get rid of this. I think we're done with that for now. Okay, so let's look at a couple other pictures. We have this one so far. The original function had a jump, and so did the derivative, and thus the derivative did not exist at that jump value. Let's look at a couple others. So here's that same one. Jump, not differentiable there. So the question, on what interval are each of the functions continuous, and in what interval are they differentiable? Well, for this first one, we would say we're continuous everywhere except 0. So x not equal to 0. We could also say from negative infinity to 0, and then also from negative infinity, and also from 0 to infinity, the open parentheses showing me don't include 0. And we're actually differentiable on that same on those same intervals. Differentiable. Same. Because everywhere over here, you're going to have a nicely defined slope. It's different at each point, but we can differentiate. Same over here. Well, here it's just always 1, so we can certainly take the derivative there. But right at 0, well, is the slope 0 or is it 1? As I talk about that limit approaching, I don't know which one it is. So, not differentiable there. Here, we've got this really funky curve situation where it's big bumps and then smaller and smaller and smaller bumps. Now, assuming there's no holes, because sometimes holes don't show up super clearly, but I think in a question like this they would show us if there was a hole. This appears to be continuous and differentiable everywhere. So here we would say for both, we're continuous and differentiable from negative infinity to infinity. There's nowhere that we have a jump or some other reason why the slope would not be something we know at that particular point. Now here's an interesting one. What's happening here is we have this really sharp turn. And so what we're going to run into the same problem that we ran into up here. What is the slope at x equals 1 at just that one point? As we approach from the left, we have a getting steeper negative slope. And then as we approach from the right, we have a steeper positive slope. But there doesn't appear to be a nice transition between those positive and negative slopes. As I just zoom in there, I can see it doesn't kind of level off. If we had a parabola and not a piecewise parabola, and it kind of has a smooth transition, negative slope, zero slope, positive slope. That doesn't happen here. You don't have that nice smooth transition from negative to positive. You just instantly switch. Negative, steep negative, steep negative, steep negative. Oh, now steep positive. There's no, how do you do that? How do you go from negative 100 to positive 100? You have to jump. And so if I were to graph the derivative, there would be a jump in that derivative. And because there's a jump, the derivative is a limit, that limit is not going to exist there. So we have another situation here where my derivative does not exist, and thus we call that not differentiable. So in C, straighten everything back out here as much as I can. Here we would be continuous everywhere because there's not a jump in the derivative. There's not a jump in the function. There's only a jump in the derivative. But we're differentiable. I'm going to abbreviate here so you don't have to watch me write with the stylus anymore. We're differentiable from negative infinity to 1 and from 1 to infinity. Everywhere except that point 1. So we have our parentheses, not our brackets, to say, well, don't include the number 1. And then in D, well, here we have what appears to be a vertical asymptote. And so the vertical asymptote, let's assume it's at 4, it looks like it, or sorry, negative 4, it looks like it is. Well, what's the slope there? You're going to have sort of the same issue you had here. I have a really big negative slope, and then a really big, well, hey, that's still actually a really big negative slope. So are we okay? Do we just go from really big negative to really big negative, and that's fine? Yes, but what about at negative 4? There's not even a function value for negative 4. So how can there be a slope there? So here we see that if the function's not defined at a particular point, well, certainly then the derivative can't be defined at that point either. So here we would be continuous. I'm going to really abbreviate, just make a C. We're continuous from negative infinity to negative 4, and then from negative 4 to infinity, and we're differentiable on that same interval. Same. Let's look at just a couple other pictures because there's one other thing that we really have to be careful of. So same question, on what interval are we continuous and differentiable? So in A, what we're looking at here is that we have these endpoints. The graph doesn't just keep going. But in between those endpoints, we have a nice smooth curve. There's no jumps, no vertical asymptotes, no sharp turns like we saw on the previous page. So here we would say we are both continuous and differentiable, C and D. Here we're going to use a bracket, and that's going to be from -1 to 6. Now, super important. We might say, well, how can you include 6? Because there's nothing over there. I can't approach, or sorry, not 6, -1, because I can't approach -1 from the left. There isn't a left-hand limit here. So in this case, when we say if there's nothing on the other side of that point, and it is a point, it's not an open circle, then we do actually include that point. Same for the 6. There's nothing over there, so it's like, well, okay, obviously there's nothing over there. So just as long as it's good at 6, which it is from the left, from the one side it can be good from, we're going to go ahead and include that point. This is the graph of a semicircle, and this is the graph of a cube root function that's just been kind of stretched vertically a little bit. And what's important for both of these? This is a function. It passes the vertical line test here. This is, again, I forget what my vertical stretch was, but it's some version y equals something a x to the 1/3. It's definitely a function. One input, one output. This is a semicircle. So this is y equals the square root of, that's going to be 9 minus x squared. Also, definitely a function for the part that it's defined for, right? You know, anything out here similar to in A, there's nothing defined there, so I'm clearly not worried about that. But in this case, this is actually a vertical tangent line. Just like this would be a horizontal tangent line, slope of 0, horizontal slope. This has to be a vertical tangent line, slope of infinity. So we would say we're not actually differentiable there because we don't have one number slope. We have an infinite slope. So in this case, we'll look at C first because it's the one I'm currently looking at. We're going to be continuous from -3 to 3. But we're going to be differentiable from -3 to 3. Don't include the endpoints because at -3, your slope is infinity. It's a vertical tangent line. If this one has a slope of 0, this one has to have a slope of infinity. Same thing happens over here, but with the cube root, there's no negative problem. So my domain is all real numbers, so I'm continuous here from -infinity to +infinity. And I'm differentiable, though, from -infinity to 0, and then from 0 to +infinity. We have this vertical tangent line that we have to worry about. Again, sometimes people are confused. How can we have a vertical tangent line and be a function? Isn't that then a vertical function? It's not. This clearly passes the vertical line test. Plug in any x, you're only going to get one x or one y out, but the slope at 0 is actually undefined. And if you want to really see it, you can do the algebra and find, put any number you want in here. Put 7, put 2, put 1 there. And actually do that derivative, and you'll see you actually will get an undefined slope for x equals 0. Okay, so we talked a lot about what is differentiable, and as we summarize what we saw here, we talked earlier in the chapter about what is continuous, but as we summarize what we see here, there's a couple things that we're looking at that make something not differentiable. So let's go ahead and write those things down. There's 3. So we're not differentiable at x equals a if f of a has a blank. So one option that we were just talking about is a vertical tangent line. If the slope at a particular place is vertical, that means the slope is undefined. Well, if the slope is undefined and the derivative tells me the slope, then the derivative is undefined, and then that's not differentiable. B, which we saw on the previous page, is that sharp corner, which we call a cusp. Corner? No. Corner, which is called a cusp. And then the other option that we saw those jumps, and we saw the vertical and we saw the vertical asymptote. So anywhere that if f of a has a jump, vertical asymptote, or even a hole, we didn't see a hole, but we'll include that here. Because we either have multiple y values to consider if we have a jump, or we have no y value to consider. And how can you have a slope at a particular y value if you don't have a y value? So all of these would just be lumped in with saying if the function is not continuous. If f is not continuous at a. Or we could have said if f is discontinuous at a. So you're going to have some questions to work on asking you about continuity and differentiability. So you are basically going to be looking for these 5 things: vertical tangent line, cusp, or jump, vertical asymptote, or hole, which we can lump all that in as a discontinuity. So if we're looking for where's the function differentiable, we're looking for, okay, where does it have these? And it's differentiable anywhere else. So first we identify the problems, and then we say, okay, well, differentiable anywhere else. One last little fun thing here I think is fun. There is a restaurant in La Jolla called Cusp, overlooking the ocean, because that nice graph that we looked at with that sharp point, doesn't that just look like a bird? You know, that classic bird that we draw on the sunset picture? I get excited when I drive by that restaurant. All right. Thanks for watching.